Hello, this is Christian Roseland with PV Magazine. We're here at the Quality Roundtable at SPI 2019, Failures, Fires, and Fiascos. So let's take a look at what's going on inside.
The room was packed with industry professionals from installers to module manufacturers and representatives of the testing and auditing environment. Kicking off the discussion, Kaushik Roy Chowdhury, technical manager at DuPont, shared his insights on the choice of backsheet materials. In a comprehensive study of over 1.8 gigawatts of modules in the field, DuPont saw that cracking, yellowing and other failure modes have caused modules to fail just after a few years in the field.
Sometimes replacement costs because of the premature failures can actually impact the system's LCOE beyond the nominal degradation. So what I'm showing here is a plot of percentage degradation or replacement costs with an increase of degradation from, say, 1% nominal degradation to a 2% nominal degradation. And the rate of LCOE increase is way less steeper than, say, if you have to replace 6% of the modules in a field versus 20% of modules in the field.
This claim of low-quality PV adding a massive bill in the long run was supported by the first quality case presented by PV Evolution Labs head of PV module business, Tristan Arion Lorico. Tristan presented a case of a solar plant which had been built in 2011. The modules showed severe burning around the cells and in some cases even melting. The problem?
They then pulled some modules and had them tested in a lab, and they saw that there was these micro cracks in the module, and in some areas the micro cracks caused isolation of the cell, and not only does it cause power loss, it causes the current to concentrate in certain areas. So this cell here with the arrows going to it, all the current of the other cells is forced into about 2/3 of the cell rather than the whole cell. So that causes the cell where it's not dark to be extremely bright, and that brightness leads to hotspots, which leads to backsheet burns.
The 5-year warranty for the modules had expired and the module manufacturer showed little will to cooperate. In the end, the asset owner had to foot the bill and replace the 1,500 modules. For technical reasons, the plant had to be partially re-engineered and the entire bill was around 200,000. That is about the entire portfolio's O&M budget. Preventing these incidents from happening is no easy task, as purely relying on IEC or UL certification will not suffice.
Even the PQP testing is not enough to catch this, because we constantly see suppliers that have passed all the tests, they have good bill of materials. Problem is, the stringing process, soldering process, is not really so stable. So it can drift, and we see it all the time. And you can have a line that is constantly, failing the build test, but they won't stop it because that has a very high cost. So if we are not there to catch this and blacklist these modules and screen them out, it's gone. You're going to have exactly the same. So unfortunately, you need certification, reliability, plus monitoring. That's how you do it. And this is very tight.
We do have a backsheet durability sequence, and we've written a white.
Tara Doyle, CCO of PV Evolution Labs, refers to the lively panel discussion after the case was presented.
Now, we just got done with 2 panels that happened at our Quality Roundtable. The first one was focused on the bill of materials. Why is this such an important matter when it comes to module performance and safety in the field?
Yeah, that's a good question. So we are seeing, as more and more gigawatts of solar are deployed worldwide, we're seeing more and more challenges and problems presenting themselves in the fields. And so what we're aiming to do at PV Evolution Labs, what we are doing is we're testing modules, inverters, storage, balance of system, but focused here on modules. We're testing at the bill of materials level so that we can detect all of those issues that might be showing up on a component level with process, with any kind of quality issues that are coming up with those components. And we're also looking at the process inside the factories of constructing these modules with these bills of materials in order to avoid those issues that are happening in the fields.
The experts present at the room took the time to analyze the solar nightmare which unfolded atop some of Walmart's roofs. The subsequent legal case against Tesla made headlines in mainstream media, causing a substantial PR damage to all of the industry. Therefore, that experts felt that it was important to address these issues, provide clarity and explain how to avoid such events.
Obviously, fires, statistically, it's so few events. Why are we really worried about this?
Because it's not statistically insignificant, because what's happening is there's been so many of them that the lawyers have these things captured and they're not going to let this stuff go public because they haven't hit a courtroom yet. So there's quite a bit happening. One of the issues we're seeing in the U.S., just this year alone, is we're at about 840 megawatts of repowering systems that are less than 3 years old.
Ouch.
And that's entire big utility fields that are just all needing to be repowered. And it's combiner boxes catching fire, it's wire harnesses leaking current, it's intermated connectors. You pick it, it's all being done wrong. And it seems like in the last 3 years, people have lost their mind and done so much stupid that the owners of these assets are now the recipients of all this junk.
Stupid is as stupid does, and that's not necessary. Brian Mills, product manager with Stoibli, explains what likely went wrong, highlighting that correct handling and installation of connectors is absolutely important to avoid the failure sequence which had unfolded atop of Walmart's roofs.
There's two things you typically see in an installation, right? There's gross issues, which are going to manifest themselves almost immediately, right? You go to power up the system, you find a problem on the strings, something like that, you fix it immediately. Hopefully you see a systemic issue, maybe you don't, right? So then you address all the gross issues you have immediately. Power up the system, everything seems okay, sign off on it. What happens is those interconnections, whether it's from cross-mating, whether it's from not appropriately connected together, whether you didn't crimp it properly, whether you didn't tighten the cable gland nut down enough, what you have is a slowly growing and manifesting problem. So if it's resistance-based, what you have is, let's say, for instance, you don't crimp the connection properly, like Dean talked about. You under-crimp it or you over-crimp it. What you have is a situation where you have air gaps in between the strandings and the body itself. You have a copper conductor, so coppers like to build oxides on the surface. Oxides create resistance, so resistance creates heat. And the physical phenomena there is heat is the fuel of chemical reactions. So now you're growing more oxide layers. More oxide layers gives you more resistance. And so what you have is a self-feeding, propagating issue that gets to a point where it runs away. And now you have an exponential growth in these oxide layers, and you have, as we do like to colorfully call, a thermal event. Thermal event can be a fire, but it mainly results in superheating of metals that then become molten, and then you have an arc, and now you're ablating and melting off molten metal. Molten metal is a great fire igniter. So these things typically take 2 to 3, maybe 4 years to manifest themselves. That's about the average cycle that I've seen.
Thank you for joining us for our coverage of PV Magazine's Quality Roundtable at SPI. We'll see you next year.